All right, here we are. Lecture 24, winter 2020, EECS 281. We're going to be talking about knapsack and shortest path algorithms. We start out with a nice cover slide here from XKCD. Some brilliant humor in XKCD. Random and row. Genius. So we look at the comic. See, there's a menu on the left, and there's a conversation going on with the people at the table and the waiter. They say, we'd like exactly $15.05 worth of appetizers, please. Exactly? The waiter's trying to figure out, how am I going to get exactly $15 worth? And the patron says, here, these papers on the knapsack problem might help you out. Waiter says, well, listen, I got other tables to deal with. And of course, to help deal with all those other tables, we could send you some papers on the traveling salesperson. So there's some good humor there. I don't think it's the last time we'll see Randall Monroe this semester, but it's always fun when we do. So we'll start out with the knapsack problem definition. Start out, you're trying to rob a safe. You get there and you find the safe filled with these items. Each item has some physical measure, whether it's a weight or a size. So in weight versions of the problem, your backpack can hold, your knapsack can hold any volume as long as it doesn't weigh too much. In the size version, it can hold only some limited size regardless of what the weight is. This is an ideal problem, but it's still worth dealing with, because it shows up in things like, how can I get as many of these packages inside a UPS truck as I'm sending it out for delivery? Or how can I pack enough things in these small boxes that are coming out from an Amazon warehouse to reduce the number of shipments that I have to make? So the knapsack problem is, you're trying to figure out how to take, of these N items that are in the safe, how can you put enough of them in your bag, your knapsack as it were, to give you the most possible value? Because after all, you are a thief robbing a safe. You would like to come home with as much value as possible. Your knapsack has some physical limitation. We'll call that capacity, and we'll use the letter M to cover that. So the capacity is sometimes weight, sometimes it's volume, but it's usually just one or the other. So the problem is to find the maximum value you can pack into the knapsack that does not exceed the capacity M. Slides not showing in the stream here. Oh, okay. Yep, I'm getting the call here. Yep. No slides, eh? Yeah. I can hear myself talking in your room. Yeah, I can hear you. It says my stream is good, and it says drop frame 0, streaming good. All right. All right. I think we have solved our problem. Thanks. All right. Love this live broadcast thing. So here we are. So many windows to watch, so many things to do. We missed Randall here. There's Randall. That should be live now. And there's a delay between my device, my other device, and the streaming platform online, and then the delay between when you send me messages. Plenty of delays here. Getting it right, always a fun thing. Okay, so there is our first slide, cover slide, talking about the Randall Monroe restaurant ordering. Next slide, we start talking about this knapsack problem. Here is the definition that I've given. A thief robbing a safe finds it filled with N items. Items have various physical measurement, whether it's weight or size, doesn't really matter. It's usually one or the other. And items have various values. The thief has some knapsack with capacity M, and then the goal is to find the maximum value that you can put in the knapsack, completely inside there, so that while walking away from the scene of the crime, you don't get caught, right? So you can't overfill the knapsack, and you want to get as much value as you can in there. Sometimes that means leaving empty space, but other times it doesn't. So we'll look at that. Here's our example. We'll use this a few different times throughout this lecture to try to set up various scenarios. We're going to start with this knapsack capacity. M is equal to 11. Then there are n different items. In this case, that n is 5. Each item has its own size and its own value. So in this case, our capacity, let's call it volume, and the size here is also measuring volume. So as I'm trying to figure this out, let's do what the humans can do really well. Sort of eyeball this and figure out what you would see as the most I could put into a bag of size 11. So if you look closely there, you'll see that I could put that 6 item in there, the 6 size item and the 5 size item. That should give me a value of 40. So if I put that in there, I can get a value 40, and that's the best I'm going to do. If any algorithm comes up with something less than 40, in this case, we're going to call it suboptimal. All right. Before we get started, though, this isn't a static problem. There's a few variations that go on in there. The first version of it, where each item is unique, that's kind of what we're looking at there. We call this the 0-1 knapsack problem, because that's sort of the binary equivalent of saying this item is in or out. It's either marked as a 0, not included in the stash, or a 1, it is included in the stash. So we can use that. That's our first variation, the common one. Another way to do it is to say these items are unique, but there's more than one copy. So that's a weird sort of way to put that. So it's a finite number of each item. So it's not exactly unique, but the finite number of them says there might be 10 of these and 5 of those and so on. So really all that is just making copies, and then we can sort of look at them as if there was 10 unique values, all of the same values, 10 unique items. So that's an explicit list version. Another version is the more infinite number of copies, and that's kind of how you think of making change when you're giving change back to somebody who just purchased something. You don't really have an infinite number of items in the change drawer, but you've got more than enough pennies, dimes, nickels, and quarters on a good day to handle any change that you need to give back. So it's effectively infinite. So some cases we do have a full infinite version. Other cases that have physical equivalents, we have enough of a stockpile so that it can behave as an infinite manner. Another variation, fractional knapsack. This is where I can take an item and divide it so that I can get part of its size and then still get part of its value. So you can imagine where some items can be subdivided and still got some value. If you've got a gold bar and you cut a gold bar in half, you have half the value. Whereas if you have a famous painting and you saw that in half, you have lost quite a bit of value. So depending on the problem domain, sometimes a fractional amount can be used. And finally, I already previously mentioned that sometimes you use weight instead of size. So in that case, you have an infinite volume but a limited weight. Or in the standard case, you have an infinite weight but limited volume. So we'll look at knapsack with our algorithm families that we've already sort of looked at before. I'm not going to do all of them because it doesn't make sense, and we'll see why. First, we'll start out with brute force. Brute force and greedy kind of go well together. They're both pretty straightforward approaches. Later, we'll look at dynamic programming and backtracking, right? We don't do divide and conquer just because divide and conquer hasn't really done anything for us. We've got a smaller bag. We need to fill that thing. So we'll look at the DP because when we've got that smaller bag, it's not a separate bag. It's an overlapping bag. So our two families that sort of take a problem and turn it into a smaller problem, dynamic programming is going to apply, whereas divide and conquer will not. Then we'll also look at backtracking and branch and bound as ways to get this done. All right. So let's start out with brute force. easiest way to do brute force is just try everything. That's what brute force does best. So I'm going to take this initial set of n items and consider all possible subsets. In our math lingo, that's called the power set. That's the set of all subsets of a collection of items. Then I'm going to divide that power set into what we call a feasible solution set. So this has only the subsets of n that actually fit inside the bag. And from those feasible sets, now I'm going to have to apply some function that says, how do I find the maximum value in the feasible set? And that's the way I do it in brute force. Brute force pseudocode here. Wonderful pseudocode when you can write exponents in there. 4i equals 1 to 2 to the n, right? Because if I've got a 0, 1 knapsack with n items, each item has two states. It can be included or it can not be included, right? So that gives me 2 to the n different values of this, different configurations of sets in the power set. So I have to loop through every single one of those. And you can see that I can, in this for loop, I'll generate the next power set. That's a possible set. Then I check to see the size of it, to see if it fits. Then I check to see the value of it. And if the size means that it fits and the value is greater than I've seen before, then I'm going to use that as my best set ever. A pretty standard sort of maximization algorithm there. I'm going to be looking for something that doesn't violate the constraint of fitting, but still gives me more value than I've seen. And since this is brute force, and it looks at all 2 to the n versions of it, this will absolutely find the best way to do this. All right? The problem with it is time, of course. We look at the efficiency of it, generating this big O of 2 to the n subsets is pretty large. After I've generated each one of those sets, that's 2 to the n work, each one of those sets is going to require me to measure it. So I'll have to look through the number of items in the set, which could be, in the worst case, all n items, or at the very least half of the items. It's always big O of n to see, does this even fit? And I've also got to figure out what's the value of the items that are included. Also a big O of n sort of thing. I can combine those two if you think about it. If I've got a loop of things, I can look through to see what their total value is and their total weight is. If the value works, then if the weight works, then I use the value. So then I end up with my brute force being something like a big O of n times 2 to the n, which is going to take quite some time. If you bring along your monkey, monkeys are great for doing brute force work because they just try everything. So if you bring along your monkey and say, hey monkey, here's the 10 items, I got to figure out the best version of this. It's going to take 10 times 2 to the n attempts to figure out what's going on here. Well, it's just 2, so I should say that 2 to the 10th, right? So there's 1,000 different combinations, and then we have to do some adding and all of that stuff for each one of those things. Basically, if you're there with brute force and monkey's helping you pack the bag, monkey's going to the zoo and you're going to jail because the police are going to catch you before you get your bag stuffed and out of there. So brute force will work. It will always work. But you can see how the efficiency on it is terrible. How about greedy? Greedy is great. Greedy works a lot faster in many cases. The problem, though, is this greedy optimality principle, when sometimes I make a decision early on that prevents me from making a better decision later, and we'll see that that doesn't always hold here. So the two approaches I have for greedy is let's go by value and let's go by size. If I take the highest value items first, then that's one greedy way to do it. I figure like I'm getting the most value every time I pick something. But if I've got really large items and they've got high value, they might be preventing me from filling my bag effectively. So I might have to say, well, I've got this one big item. It's the highest value item, but it uses up so much of my bag that I can't put anything else in there. And in the case where I could put two medium-sized items in there, they're both worth less than the main item, but together they're worth more. That would be a way that the greedy approach would fail. You say, okay, well, let's not stick big things in there. We'll put small things in there, because the smaller things that we put in there, the more things we can put in to the bag. However, if I get a bunch of little cheap little items, I got my bag full of trinkets, I got one nice solid gold bar at the end of the pack that doesn't fit, then I'm going to be missing out. Oh, okay. So a couple of questions here. How is the next set from the power set generated? Oh, that's the beauty of pseudocode. You can just wave your hands and say that thing has happened. But there's ways to do that, and similar algorithms to something like genperms, which is going to give you all the permutations, right? We've got an algorithm that's going to give you the next power set, as well as the question of why does it take linear time to filter feasible solution sets, right? So if I've got a feasible solution set, say there's n items, and I pick 8 of them, if I'm going to figure out what is the size of those 8 items, I have to add each one of their sizes up, which is going to take me, 8 looks at values. And 8, is on the order of 10. In the worst case, I've got all 10 of them. So that's why it's a big O of n. In the worst case, as you look at all of the items that you've picked, it could be all the items. Now you have to spend a linear amount of time to see what their size is. You also have to spend a linear amount of time to sum their values as well. You can do that size check and value sum all in the same loop, but it is going to be, in the worst case, a big O of n loop to get that done. All right? So, how does the straightforward next step look, right? We say, well, if going by value doesn't work for me all the time, and going by size doesn't work for me all the time, let's go by value density. Let's take the ratio of value to size. And if I choose the highest ratio first, then that's about the best I can do, isn't it? Well, let's see. All right, so here I have that initial set of things that we came up with, the value on items sized 1, 2, 5, 6, and 7. We already decided that our optimal value here is 40. Anything that shows up less than 40 isn't going to work. So we'll start out with greedy by value. Greedy by value is going to say, let's take the highest value item, and I'll put that in there. That takes up 7 of my spaces. Now I've got 28 value in there, and in terms of what size I have left, I've only got 4 spaces left. All right, so this one doesn't fit. This one doesn't fit. 6 and 5 are too large to go in there. So I'll then end up sticking this thing in there because that's the one in the greedy way that doesn't violate any constraints. It's worth the most value and it fits. So I put that in there. It gives me a value of 6 more and takes up 2 of my spaces. And I'm down to 2 spaces. And I end up being able to stick one of these in there as well. So that'll give me a value of 1 there. And I'll end up walking back with what looks like 35 and even 1 extra space in my bag. So you get back to the clubhouse and all the other really smart thieves are just laughing at you. They say, you only got 35 with a bag like that? You should have gotten 40. You even came back with air. Who steals air? Okay, so greedy by value, in this case, didn't work. All right, so if it ever works out to a situation where we can prove that it doesn't work, then we can say that it doesn't work all the time, right? So let's try it again, and this time by size. I say, well, this time I'm going to put the small items in there because I can get more items that way. So the first thing we put in there is our item of size 1, right? That gives me a value of 1, and it leaves me with 10 spots left. All right, so then I'll stick the next thing in there. That's a size 2. It's got a value of 6. And it's going to take up 2 of my spots, and I'll end up with 8 spots left. Working from small to large then, I take the next item. That's an 18. I'll slap that in there. It uses up 5 of my spaces, and I'm left with 3 spaces left. The 6 size item doesn't fit. The 7 size item doesn't fit. I walk back to the clubhouse, and as they're snickering at our greedy by value person, walking out, head hung in shame with only 35 value, and I slap my bag on the table and it's only got a 25 value. Oh, the shame. All right, so greedy by value didn't work for us, or we found a case where it didn't work, so we can say that it doesn't always work. Greedy by size also didn't. Say, what about this greedy by ratio? That sounds like it's a lot smarter way to do things. I'm getting the most bang for my buck, literally. So let's clear up and try that one again. Those of you who are looking ahead like humans do, you see we're already going down the wrong path, right? So greedy by value density, I'm going to be using this ratio column to make my choices. So I start by picking the highest value density. That's this one here, of course. So what that puts in there is a 28 in my bag. It eats up 7 of my spaces. I got 4 left. This next one doesn't fit, and we end up with the 2 that we had before. So I had this whole wonderful new algorithm, and I still end up with 1 error and 35 value. So no matter how I've cut it here, greedy has not gotten it done for me. Greedy by value, greedy by size, or even by value density, it just hasn't worked for me. So we can say that greedy was fairly fast, however, right? Looking at our greedy pseudocode here, you can see that the pseudocode that we've got here is showing you the value density version. So in this case, we're going to have to build this ratio, takes the value array input, the size array input, does the division, turns it into a ratio input, ratio vector. Then we sort all of those things. We have to sort them by ratio so that we can greedily accept the highest value one. And from there, we've got this simple for loop. I go from 1 to n and say, hey, if this thing fits, I take it, right? If it fits, if size of I plus the current size is less than my total bag weight, then add the size of I to my current size, add the value of that item, and then keep going. So once I get past all of the setup work, this is linear in n. Much faster than dealing with monkeys and greedy stuff. Or sorry, monkeys and brute force stuff. But what was the other stuff, right? Well, for starters, I had to sort the items by ratio of value to size. That was my heavy lifting on the previous one. Going through and linearly calculating my ratios, not really that bad. It was a big O of n. And then choosing the item with the highest ratio first. I just go through this. So I end up with n log n to do my sort, plus the big O of n sticking things in the bag. Add those together, I still end up with big O of n log n. So I went from n times 2 to the n down to a tiny n log n. However, even though my brute force efficiency was low, it was guaranteed to find the best solution because it looked at every possible solution. Here, though, we see how the greedy solution has prevented us from looking at some other solutions. And in that case, has prevented us from finding the actual best bag. So there's a couple of problems with our first 2 approaches. One, too slow. The other one is much faster, but it is not giving me the optimal answer. As a side note here, if we change the problem up just a little bit, looking at the fractional knapsack on the greedy algorithm. Fractional knapsack, remember, I can take a portion of an item and still get that ratio's worth of value. That ends up working out great, right? So in the case of my previous version, I would have taken that 7 size item and gotten 28 value out of it. And then with only 4 spaces left, I could take the 6 item, right? But in this case, I'm going to multiply it by 2/3. And if we look at that one was worth 22. So that'll take 22 and I multiply that by 2/3. And I add those things together and I end up with something that looks like 42 and 2/3. Now, that is awesome. Did I get that right? 42 and 2/3. That's more than the 40, right? So in terms of what we're looking for. If I can't subdivide them, 40 was my optimal. But if I can go fractional, a greedy algorithm is going to work. It is going to work because you never choose anything that prevents you from getting something better later. You start with the highest value density ratio, take as much of that as possible, and then you move to the next thing. Take as much of the next value as possible. And so you end up with a bag that's absolutely full of the most value dense items that you can possibly get. So fractional knapsack does work, but it only works, the greedy algorithm does work, but it only works when I've got the ability to go fractional in this knapsack. All right, now let's get into DP. We just talked about DP a couple of days ago. So now we're going to try to apply this dynamic programming approach. First, we'll look at sort of a simple recursive version of it, just to make sense out of a problem solution. Once we've got a nice recursive problem solution, then we can easily convert that to a recursive DP solution. We'll also look at a bottom-up iterative version of that as well. So we should be able to manage this. And the last caveat at the bottom of the page here says, just for simplicity's sake, we're going to assume an infinite amount of each item. We could do this without having an infinite amount of each item, but it just makes it a lot more complicated code in terms of having to do the bookkeeping of whether an item has been used or not. It doesn't really change the approach or how dynamic programming works. It just makes it more complicated to discuss in a lecture. So as an advanced topic, you can implement a DP solution on Knapsack that doesn't assume an infinite amount of each item and see how you can make that work. So here's my recursive approach. First, I'm going to stick the item in the knapsack for each item. Each item, once I put the item in there, what that does is it sort of makes me feel like I've got a smaller knapsack. So I got a knapsack that's empty of size 10. I put an item in there that's size 3. It's like, okay, well, I've got so much value. Now all I have to do is fill this knapsack of size 7 because I've taken 3 of those slots. So that's how we're going to do that. For each item, we'll place an item in the knapsack. It makes it look like I've got a smaller knapsack with some now added value. And then in the end, I just remember the best packing and it's good. It's a direct recursive solution and it takes exponential time. Here it is. We see we got knapsack in line 1. It, of course, calls knapsack in line 6. So there is my recursion. Recursion isn't going to work for me if I don't have some way to get out of this deal. And you can see that I've got this for loop, so eventually I will stop recursing. I just need to make sure that I is somehow approaching n eventually. And since I'm in a for loop, every time I go through the for loop is going to make I larger. Eventually I has to get to n. That's going to stop recursing. So this is a different type of base case for our standard sort of recursive algorithms, where I usually have a recursive algorithm. The first thing I do, I've got some test that I'm ready to jump out at. In this case, I'm going to go straight into a loop that eventually will fail. So this does have a base case built into it. It does have a way to get out to prevent you from recursing infinitely. So as it mentioned in the setup, it said for each item, that's my for loop there, for I equals 0 up to n. For each item, what I'm going to do is try to stick that item in there. I say space is equal to the capacity minus this particular item. Does it fit? If it fits, then we try to fill a smaller bag, right? That's where the recursive call to knapsack of space is, because space is now the reduced size bag minus the space used from the current item. And then we add the total value from that item to what the answer of that smaller bag gives us. Really straightforward, but it is, as mentioned, exponential and painfully slow. So there's our recursive implementation. Now let's see if we can't DP this thing. And we knew we could. DP from a recursive solution is really straightforward. I need to add one line near the end. That's what this line 12 is. It says instead of returning this max, let's write it into our memo and then return it. That's the first step. And then the second step is, now that I know that I've got some values in this max known thing, when I come in, if that value is already filled out, or in this case, if it's empty, I'm going to return what that maximum known is. All right, so there's DP, because these red lines are going to prevent me from doing this work in here multiple times when it's always the same. So that's great. First, check if the requested value has been calculated. Otherwise, calculate it and save it. This changes my runtime down to MN, which is pretty nice. Big O of M times big O of N. And where does that come from? Well, I've obviously got the big O of N right there staring at me. It's a for loop of size N. How do I know that this isn't going to be called more than M times? Well, M being the size of my bag, if I'm putting things in there one at a time, the worst I can do is spend time for each slot, as you will, each one of those M values. So that's a hand-wavy kind of explanation of it. But that's the rough version of it, right? Because the worst case, I'm going to put something in there of size 1, and then I'm going to do N work to find that the next thing I want to insert is a thing of size 1, and I do N work to find that I want to put in there another thing of size 1. By the time I get that done, I can only do that M times before the bag is filled. So there you go. Our approach now has improved from exponential to something that looks linear in M times N. All right? Here's our bottom-up approach. This one is very clearly MN. And you can see it because there's not a lot of interesting things. Then there's a for loop, some constant work, and a nested for loop. And inside of here, this is all just comparisons and arithmetic. All right, so it's a constant amount of work inside the inner for loop. The inner for loop is of size N. The outer for loop goes all the way up to capacity. Capacity, of course, here is M. So my outer for loop is M. My inner for loop is N. M times N, big O, MN. Great. What does this one do? Well, it starts out by giving me a vector to put my values in, right? And I'm going to set this up to be capacity plus 1. That's my standard DP giving me one more frame in the direction that I'm programming. I'm programming towards a bag of size M. So I need to be able to square brackets M when I get done. So my size then has to be size M plus 1. So that's where capacity plus 1 comes in. And as I loop through each one of those things, I'm going to start at 1. Why is that? I start at 0. Well, 0 already has a value of 0. That's what the initialization in line 3 did. Initialize all the values to 0. And if I think about it, my bag of size 0 having a value of size 0 makes good sense. You can't put anything in there. You certainly isn't worth anything, right? Then the next version of this goes through and says, I'm going to say that as I go to the next bag, the next size up, I can always just put the smaller bag in there, right? So I'm trying to figure out the best one size bag. In line 5, I'm going to insert my best 0 size bag in there and say, well, that's the start. We can start with that, which doesn't seem very impressive here when we're talking about an empty bag. But if you take that a step farther, you say, well, when I'm trying to figure out a bag of size 6, if I've already calculated the absolute best size 5 bag, I can at the very least stick my size 5 bag into my size 6 bag, and I know that that's a good place to start. So that's what we do in line 5. We say, let's take this newer, bigger bag and put the smaller bag in there that has its already best value. And so that's how DP also survives. DP survives because it builds up these smaller solutions that are already optimal. So I've got a bag 5 that's full and perfect. Then when I go to calculate 6, I know that there's no better way to get 5. I'll just take my bag 5 out of the memo and put that in there and start trying to see if I can improve that with just one more space. And that's what my inner loop does. My inner loop says, well, if I've got that one smaller bag in there, now I'm going to try to stick each one of the items into the bag as well. some of them will fit, some of them won't fit, right? So if I've got a bag of size 6, right? Let's draw ourselves a nice 6 size bag, right? If I got a bag of size 6 here, and I put a bag inside it of size 5, right? Then there is space in here for one more item. If I've got an item that's size 1, I can put it in there, and that's going to add more value, and I'll say, hey, that's an improvement because it's more than the value of the 5 bag. That's great. Now, if I've got an item of size 2, it will not fit in the size 6 bag with the size 5 bag. But if I get rid of the size 5 bag and say, let's put the size 4 bag in there, now I can insert an item of size 2. And that's what this algorithm does. It continually looks for smaller bags to accommodate more items, right? So now if I've got an item of size 3, right, I can put that in there as long as my item of size 3 is being combined with my best bag of size 3. Those two are going to give me a full bag of size 6, right? And so this inner loop looks through each one of the items in line 6 for j equals 0 up to n, looking at all n of the items, and I say, hey, let me put that thing in there. If it fits, great. I'll just add the value. If it doesn't fit, I'll take out whatever best bag I have in there and try to put in a smaller best bag and see if that works. And remember, this is how DP survives. DP already knows the best 5 bag, but if it knows the best 5 bag, then it also knows the best 4 bag, it knows the best 3 bag, it knows the best 2 bag, and that's the best 1 bag. And of course, the empty bag doesn't do us anything. So as I say I've got a 6, I'll start out with putting a 5 bag in there and say, hey, this is great. Can I put a size 1 item in there? Yes, it's an improvement. I'll take that as my best. Now if I try to put the size 2 item in there, I have to remove the size 5 bag and put the best 4 bag in there. And if the best 4 bag plus a 2 item is worth more than the best 5 bag plus a 1 item, then that's my best 6 bag. And that's what goes on here. If I ever get to a situation where I've got enough space and the item goes in there, if that value is better than the max known for this particular one, I'm working on my new bag, I'm going to say the new bag is updated by taking the value of this current item that I'm looking at and then the max known of the remaining space, right? So in this case, as I in my previous example, I'm saying if I'm trying to fill the 6, I'm going to take this item that's size 1 and then take the best 5 bag there. Or I'll take the item that's size 2 with the best 4 bag. Or the item that's size 3 with the best 3 bag, and so on. That's how this algorithm works. It's a good one to understand, so make sure you type this in, run through some simple examples, take the 5 values from the version that we already have given, the example we've already used in this lecture, plug them in, and just watch this code in a debugger. Print some stuff out, and you'll see how your memo gets built up, how the values get built up in there, right? I think I've even got time to do that. Let's give this a run, right? Always like to do this one. This one's fun. So I'll need a slide for that. There we go. So here I am, and what I'm going to do is bring it back. There we go. We'll fix it. All right, so let's go back to what I had. I had a bag size 1, 2, 5, 6, and 7. It had values 1, 6, 18, 22, and 28. All right. So to make this happen, in terms of DP, what I'm going to do is set up my memo. My memo has to go from 0 up to and including my actual bag size. 4, 5, 6, 7, 8, 9, 10, and 11. So there we go. And I say that the value of the 0 bag is, of course, 0. Those other items also have, this is size, and this is value. Those other items also have zeros in them, but rather than having to erase, I'm going to say that I initialize this thing to 0, and I'm going to write down the zeros that I care about. So, for starters, what I try to do is I try to fill this best bag of size 1 now. So I stick the 0 bag inside there. It's got value 0, and I'm going to loop through each one of these items to say, can I put this 1 in a 1 bag with a 0 bag in there? Sure I can. It gives me a value of 1. Then I try to stick the 2 item in there. It doesn't fit because it's bigger than the bag. 5, 6, and 7, they don't fit. So I'm going to go through this loop. I'm going to go through my outer loop. Here's my M loop. And each time I'm at a new position, I'm going to go through each one of these things. All right. Next up, I say I've got the best 1 bag that I could possibly have. It's got value 1. Okay, let's try the size 2 bag. So for the size 2 bag, I'm going to stick the value 1 bag in there and say, now I've got 1 space left. Let's try to fill that 1 space. I can fill it with this 1. That's great. That's going to give me a value of 2. Okay, that's an improvement. Now let's look at the 2 item. Well, I can put the 2 item in the 2 bag, but only if I include the best 0 size bag. So that looks like it's got a 2 item for a value 6 plus the best 0 bag, which is 0. But that's an improvement in my total value. I've got a 6, which is my best 2 bag. Then I try the 5, 6, and 7. None of them fit in the 2 bag, and so I'm done with that iteration. Next up, I move to the 3 bag. 3 bag, I instantly stuff a 2 bag in there and say, well, I've got to at least get 6. I can do that, no problem. As I work my way through the N items, I say, can I stick this 1 item into a 3 bag? Sure I can. I'll put the 1 item into a 3 bag with the very best 2 bag, and that looks like I can get an improvement. I can get 7 in there. That's amazing. How about sticking a 2 item in the 3 bag? I can stick a 2 item in the 3 bag, but only if I use the best 1 bag along with it. So as I do that, you'll see that I end up with another 6 plus 1 or 7, which is not an improvement. So I'll just leave that alone. And I end up finding out that my best 3 bag is 7 value. Okay, next up, the 4 bag. Start out, stick that 3 bag in there. It's good. I'll loop through each one of my N items. Say, well, I can add 1. I can always add 1. That's great. That gives me 8. Now, if I want to stick in this 2 item, because that's next in my N loop, the only way I can stick a 2 item into a 4 bag is if I take the best 2 bag. So I'll take this 2 item for 6 and the best 2 bag for 6 and say, well, that's 12 and an improvement. So I can get to a 4 bag in 12. The rest of my N loop doesn't fit. Pretty boring in the beginning. So 5, 6, and 7 don't make any improvements. We're good. Next up, the 5 bag. We'll stick in the best 4 bag. We'll start out with a 12. That's good. Our N loop says, let's look at this first 1. We can always add that 1. That gives me 13, which is an improvement. Now, if I'm going to try to stick this 2 item in the 5 bag, I'm only going to be able to do it with my best 3 bag. My best 3 bag here has a value 7, and this 2 item has a value 6. Total value 13. No improvement. I move on. 5 item finally fits. I can put a 5 item in a 5 bag and include my best 0 bag with that. And this looks to be 18 and an even better version of this bag. Great. As I try to fit the 6 and 7 from the rest of the N loop in there, they don't fit. I move on saying, I know for a fact the best 5 bag has a value of 18. At 6, we'll bring in the 5 bag. That's good. And then we'll try to improve upon that. Of course, I can always add the 1 item in there. That gives me a 19 value, the best 5 bag plus a 1 item. Then as I try to stick the 2 item in there, the 2 item has a size 2, so to get that in a 6 bag, if I can combine that with the best 4 bag, that's going to be the best I can do with the 2 items. So that's a 6 value, a 12 value, 18 doesn't improve 6, so I move on. How about this 18 here in the 5 bag? Well, the 5 item. The 5 item plus the best 1 bag gives me another version of this 19, right? Because I'm adding the 1 item to the best 5 bag or a 5 item to the best 1 bag, and they're really only just a combination of the 1 and 5 items. So not an improvement, so I move on. Now I try the 6 item. 6 item fits with the best 0 bag combined looks like a value of 22, and that's an improvement. So I think you're starting to see the pattern here. I'm going to speed these up just a little bit. The 7 item, of course, doesn't fit in the 6 bag. 7 is the first place where I can start to choose to try every single item as an improvement in terms of it actually fitting. So 7 starts out at 22. For 1, it goes to 23. If I try to put a 6 item, the 2 item with a 5 bag, see here that the 2 item lines up with my best 5 bag, 6 and 18, actually give me 24. There's an improvement. The 5 item goes into the 7 bag with the best 2 bag, which is another copy of that 24, no improvement. The 6 item goes in with my best 1 bag, which is 23, that's a decrease. And then lastly, I can stick this 7 item in with the best 0 bag for a 28. And there's my best 7 bag. So you can see here, DP is going to go through, build up all of these things, and I've got this solution that's going and going and going. And every time that I need to know something smaller, because I've got this overlapping solution, is, well, I needed to see that best 4 bag again. I don't recalculate it. I go look it up. Yay, memo. All right. So 8 sticks in the 28, upgrades that to 29 for 1. The 2 with the 6 bag gives me a 28, no improvement. The 5 with the 3 bag gives me a 25, no improvement. The 6 with a 2 bag gives me a 28, no improvement. And then lastly, the 7 with the 1 bag gives me a 29, also no improvement. So there's my best 8 bag is a 29. I'll bring my best 8 bag to make my best 9 bag and instantly upgrade that to a 30 to try the 1 item. The 2 item on a 7 gives me this 2 item 7 bag. We'll call that a 34 for 9. That's pretty good. The 5 item goes up against the 4 bag for a 30, and that's not impressive. And the 6 item goes up against the best 3 bag. Go away. 6 item goes against the 3 bag. That's a 29, not an improvement. 7 item versus 2 bag gives me back to that 34. So 34, my drop dead best way to get 9 items in there, right? 34 for 10, 35 plus the 1. Then I add the 2 item to an 8 bag. That gives me a 35 again, no improvement. I can add the 5 item to a 5 bag. That's a 36. That's good. And the 6 item goes into the 4 bag, which is a 34, no improvement. I can put the 7 item in to the 3 bag, which is a 35, not an improvement. All right, we're rounding home here. Rounding third, headed for home. 36, add 1, we get the 37 bag right off the top because we can add that 1 item to the best 10 bag. Then as I try to add this 2 item to the best 9 bag, you see that 34 plus 6 is 40, and we remember 40 is optimal. We're not going to get any better than that, but our algorithm doesn't know it. So we keep moving. 5 item with the 6 bag. Hey, look, there's another 40. What is a 6 item with a 5 bag? Yeah, there's another 40. Oh, I looked at 40 3 times. And lastly, I've got this 7 item with the 4 bag, which is, of course, 40. All right. So in the end, I look at square brackets 11 in my memo, and it tells me 40. So that's how DP works. You had a chance to see a DP solution, and this was clearly bottom up, right? We started with an iterative loop, and we started from 0, went to 1 to 2 to 3 to 4 to 5, all the way up to n. So this is the dynamic programming approach to solving 0-1 knapsack. All right. I think I still have to wrestle with my... There we go. I'm good here, right? Yep, there we go. Let's go to 2 more algorithm families, backtracking and branch and bound. Well, backtracking, we can instantly throw that one away. Because backtracking, we remember, that's useful for constraint satisfaction problems. And constraint satisfaction problem is there a way that I can fill this knapsack without overflowing it? Yes? Okay, we're done. That's what backtracking will give you. Backtracking can show me all of the different ways I can put things in there, but it's not going to give me an optimal solution because it's not an optimizing algorithm. That's why we're going to use branch and bound, because remember, branch and bound takes backtracking and adds an additional sort of constraint to it. It's like, hey, I'm looking for something that will solve it, but I'm looking for something that's going to solve it even better than I've already solved it. And if this current solution that you're offering isn't an improvement, then I'm going to add that as a constraint fail, because I'm only looking for the best solution. So we could use branch and bound. We can't use backtracking. How do we get to an initial estimate? Right? Now, the thing about this one is, with all the work that we've done recently in Project 4, Project 4 is a branch and bound algorithm, and the way that we've taught it, we've done this upper bound, lower bound thing. But we're doing that in the guise of traveling salesperson. And traveling salesperson is at heart a minimization algorithm. We're trying to minimize the total path covered in the traveling salesperson. Knapsack, on the other hand, that's a maximization algorithm. We're trying to see how much can I actually get into this bag. So everything gets flipped over on its head, right? When I've got some initial solution as my best, this isn't an upper bound now, it's a lower bound, right? Because unless you're going to get down below that, I'm not going to consider you as a better solution. I said that backwards. It's so easy to get these things backwards, right? So our initial estimate is a lower bound, because if I end up with something less than that, it is clearly not optimal, right? So in the TSP, we're going to say our initial estimate is an upper bound, because if we're going to spend more than that, it's already a bad idea. So we're trying to minimize and get less than that. In the reverse version of it, when we're maximizing, I'll start out with a lower bound, and if I don't get above that, then it's not worth my time, because I've already got something that's at that value, right? Then what's left? We're going to figure out what the upper bound is. And remember how in TSP we had our lower bound, because that's what's estimating what work needs to be done. And our lower bound, we wanted that to always be what? Less than actual, right? Because if it was less than actual and it looked bad, actual would be even worse. And so we could definitely throw this away. So when we flipped everything over and we're now using an upper bound to figure out how much work I might have to do, it has to be longer than actual, because if it's longer than actual and we decide it's bad, in reality, it's going to be less, and that's going to be keeping us from having the solution. So we have this upper bound to see how do we get this bag fixed, right? And in the end, if the value that I'm looking at is less than what I've seen so far, then I want to throw that away. Okay. All right. Don't spend too much time thinking about how this one works if you're still fighting with Project 4, because as you try to flip upper bounds and lower bounds around in your mind, and initial estimates being this and that, it can be really complicated. But make sure that once you've got your Project 4 done, that you try to approach a maximization solution with a branch and bound algorithm, so that you understand why the estimates are lower bounds from the start, and then our work estimate is going to be an upper bound, and then figure out how these things work. All right. So here's my summary. I've got the knapsack problem. We looked at it with these 5 different approaches: brute force and greedy. Brute force always found the optimal solution, but it often took too long. Greedy was much faster, but depending on the data, it might not find an optimal solution. DP was great. DP ended up with something that was very serviceable in terms of time complexity. Big O, M times N. And it got us an optimal solution. So that was really great. Backtracking didn't apply because it wasn't going to give us a best. And branch and bound, of course, always looks bad from a complexity standpoint, because it doesn't change the complexity. Remember, Branch and bound doesn't change the complexity, so it still looks exponential. However, it does end up working much faster than that in practice. How much faster? Very hard to say. That is a task for a class like EECS 477. Algorithms. Speaking of algorithms, let's change gears a bit here. So this is part 2 of this lecture. First part was knapsack. Second part, okay. Well, that just happened. So, shortest path algorithms here. That's what's coming up next here. And our cover slide has some airline routes. You can see them, a bunch of lines drawn from hubs, flying things. And that's going to sort of give us the flavor of this thing. Some shortest path examples from real life, obviously, are traveling somewhere on our highway system and things that you can optimize in those paths. Those paths are, I want the shortest distance, or I want the shortest travel time. This is something that you see when you look something up in Google Maps or any one of your map applications. It'll tell you, you want to go from here to there. Do you want to avoid toll roads? Do you want to avoid surface roads? Use only surface roads and things like that. So different ways to sort of flavor the problem. How about if I avoid the number of stoplights? That's something that UPS would like to do. Right? If you look at the UPS driver's route, they avoid stoplights as many as possible, and they make as many right turns as possible. Left turns are slower. Stop lights are slower than stop signs. So shortest path might mean physical distance. It might mean travel time. It might mean any number of things. The writer of this slide was a big fan of Krispy Kremes. So our shortest path that gets me there, going through as many Krispy Kremes as possible, or something along those lines. That's what's going on there. Another thing that does it, a network of airports. You can, of course, see that when you get your frequent flyer miles. Sometimes travel time is better. Sometimes your layover time is better. Actual distance is important. Sometimes it's fares. All of these things go into booking your flights. So what is a weighted path length? Here's our definition. Given some edge-weighted graph, G, with a set of vertices and edges, V and E, then I've got some function that tells me or some lookup where I can see the weight of the edge connecting some vertex to some other vertex. So we'll call that C of V sub I and V sub J, the weight of those connecting edges. So in that case, then, a path is some non-empty sequence of vertices that goes from vertex 1 to vertex 2 to vertex 3, ... all the way up to the kth vertex. And the weighted path length, then, is just the sum of all of those k edges, k minus 1 edges, really. There's k vertices, there's k minus 1 edges. The sum of those k minus 1 edges, and we'll use that C function to get that value. So that's my weighted path definition. The general problem, then, is given some edge-weighted graph, and I got two vertices, my V sub S, where I start, and my V sub D, where my destination is going to be. I want to find the path that starts at V sub S and ends at V sub D, has the smallest weighted path length. There we go. We call this the single source shortest path problem. And it turns out that to find the shortest path from V sub S to V sub D, that we have to find the shortest path from V sub S to everywhere. Right? And that has dynamic programming in its roots. Right? So if I'm trying to find the shortest path from V sub S and to V sub D, and I just find one of them, I say, well, this is the shortest. Well, you don't know that it's the shortest. Maybe if you went through this other point, it could be shorter. Oh, okay. Well, now I found a second one. That one's shorter. That must be the shortest. Well, maybe there's some other point that I have to go through to get to the shortest version of it. So this is why we find the shortest path from V sub S to everywhere, because the program doesn't know until I found the shortest distance from V sub S to everywhere that every other place might just be one edge away from V sub D, and that edge could be shorter than the current best to V sub D. So our single source shortest path, Dijkstra's algorithm, which was developed after dynamic programming and uses elements of dynamic programming to get it done, our Dijkstra's algorithm is going to find this single source shortest path by getting v sub s distance, the distance from v sub s to everywhere, and then that will know that we've got the best way to get to v sub d. For some definitions, I can see here that I've got a directed weighted graph, and this works with directed weighted graphs. It works with undirected weighted graphs as well, but we do have to have weights in order for us to minimize. So if I'm just looking at the total number of edges, then there's no real way to do this. There's no difficult way to do this. It's pretty easy. So here's my shortest weighted path, and it's already drawn out for me, BACEF. So we can see that just as we move forward. You see here's the shortest unweighted path. It's just counting the total number of edges. It's a completely different problem. BCEF, that's just how many layovers do you have in your flight. Sometimes you don't care how long you actually fly in the sky, as long as I don't have to take too many layovers, right? Shortest path problems are generally undefined for graphs with negative cost cycles. Aha, got there. Shortest path problem is undefined because if I just keep going around this triangle that you see highlighted here from from D to A to C back to D, I'm incurring 6 while going out and making up 8 while coming back. And so I can make any path cost 0 as long as I do enough loops around DAC, 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 DAC. So that is unrealistic. So our shortest path problems are undefined for graphs with negative cost cycles. You can't do it, right? So here's Dijkstra's algorithm. It's a greedy algorithm that uses aspects of dynamic programming, and it solves the shortest path problem. We start out, we assume non-negative weights, and we're going to find the shortest path from v sub s to every other vertex. This should look a little familiar to you because for each vertex, you will need to know the k sub v, the d sub v, and the p sub v. K, do we know the shortest path? K is in known. D, what is the length of the distance of that path? And then P, what vertex precedes that path? All right, so the question we have is, how are these problems different from the TSP? In the TSP, I need to get back home. And I have the further constraint of not being able to go through any place twice. However, in the shortest path, I'm just trying to get from A to point B, as it were, even if there's many other points in between. All right? So, K sub D, K sub V, D sub V, and P sub V should look a lot like Prim's algorithm because they have almost identical meanings as they do in the Prim's algorithm. There's just one small little addition that we add, and it goes from being Prim's algorithm to Dijkstra's algorithm. All right? So here is my graph. We simplified it. We've just used the undirected version. And if you look closely, you can see that BACEF, that is still my optimal version of getting from B to F. That's my goal here, to go from B to F. And if I go from B to A to C to E to F, I should end up with something that looks like a distance of 9. All right. So we'll start out in Dijkstra's algorithm, and we get to Dijkstra's algorithm by setting some distance equal to 0, and we jump into our basic Prim's loop, right? So in this case, I'm going to set my starting location, my v sub s. I'll set v sub s, set its distance to 0, and then I'll run through my standard Prim's loop, and I'll make a change in the future, right? So there I say, let's find the shortest one, and I've got infinity, 0, oh, infinity, infinity, infinity. It must be this one. So we'll mark this one as true and say that its distance is 0. It has no predecessor. And now I want to update everything that can be reached from B, right? B lets me reach A and C. And as I go to set the distance to A, in Prim's algorithm, I would set that distance to 3 because the edge between B and A is 3. In Dijkstra's algorithm, however, I'm going to set that edge to be 0 plus 3, which is drastically different, right? Wrong spot. And there's ESPN giving me notifications too. All right. So I'm going to set this distance to A to 3. And that 3, to be clear, is not just the edge from B to A. It's actually the cost that it is for me to get to B plus the cost it is for me to get to A. So since B is my starting point, it's got a 0 in there. It's going to look exactly in this first step as if I was doing prims. And I got to A by going from B. The same thing is true from C. Instead of just putting 5 there, I'm really putting 0 plus 5. Because it cost me 0 to get to B plus the distance to go from B to C, which is 5. And they both came from B. All right? Very similar to prims. And we'll see as we go through further steps how that one little addition makes all the difference in the world. So I'll clean up my slide a little bit. You see I've marked B as true, so we've changed the color on it, and I've more finalized the distances from V sub S to A now. V sub S to A is 3, V sub S to C is 5. All right, next up I go through this loop, find the false value with the shortest distance, and it's right here. So I'm going to be updating this one by saying let's first mark it as true, and then find all of the neighbors of A that are still false. Because anything that's already marked as true, we've already found the shortest distance from V sub S to that vertex. So as I update things around A, you see that A is only adjacent to B, C, and D. B is already true, so I just need to update C and D. The distance from A to C is 1, but that's not what I update C with. I don't update C with 1. I update C with the cost it was to get to A plus 1, which is 4, and that's an improvement. The cost from A to D is, of course, an improvement because D is infinity. But what is the cost to get to D? It's not 5. It's the cost to get to A plus the cost to get to D from A. So that's going to be an 8. So I'll call this 3 plus 5, or 8, right? And I get to there through A now. Both of these got updated because I'm going through A now instead of B. All right, that's what it looks like. Clean up, mark, looking good, looking good. Next step, same as before. This is just like prims. Remember, the only thing that I'm doing differently is instead of just adding the edge weight, I'm going to add the vertex's own distance plus the edge weight to the new vertex's shortest distance, right? So searching for the shortest false, that gives me C. I'll work from there, making sure that I add 4 to everything of interest. C is adjacent to A, B, D, and E, but A and B are already marked as true, so I only need to update D and E. C to D is 2, plus the cost of 4 to get to C gives me a 4 plus 2, which that's an improvement, right? 4 plus 2 is 6, and now I'll be getting to D not through A, but through C. All right, C to E, it's going to be improvement because E is already at infinity. So it cost me 4 to get to C and 4 more to get to E. That looks like it's 8. That's an improvement over infinity. We come through C. All right, iteration complete. Next version, I'm going to find the shortest true value, or sorry, shortest false value. That's this 6. Set that as my current point. And remember that I've got to add 6 to anything that I update from D. D is only adjacent to F in terms of things that are still marked as false. D is adjacent to A and C, but they're already true. We already know the shortest distances from V sub S to A and the shortest distance from V sub S to C, so I can't make any improvements there. I only need to look forward. So D adjacent to F says, as long as I add D's source cost, 6, plus the edge between D and F, 5, 6 plus 5, that's 11. That is not an improvement. Oh, wait, I'm on E. I'm on the wrong deal here. Wrong deal. D is not adjacent to E. D is adjacent to F. D being adjacent to F says D's source cost, 6 plus 5, that's 11. That's an improvement, right? And we'll say that we'll get there through D. And that's the only thing D's adjacent to, and that's all we have to clean up. Next shortest vertex here that's marked false, that's E. We'll take this as a source value of 8. E can get me to F for a cost of 8 plus 1. That's an improvement there of 9, and it, of course, comes through E. So I'll mark that as true. And lastly, there's nothing to do, right? F is not adjacent to anything that isn't already found. So my last step, I just marked that one as true. So there is my Dijkstra's table. As I mentioned, this looks a lot like a Prim's table. I've got the K, the D, and the P, and they mean almost the same things. But at the end of working on Prims, I could add up this entire D sub V column and say, what is the weight of my MST? That column means something different now. The P column is the same. When I connect some edge, how do I connect it? How do I connect some vertex from its parent vertex? But now I can't add all of these things up. That wouldn't make sense. What these things are is the total cost from V sub S to A, the total cost from V sub S to B, the total cost of V sub S to D to E to F. So if I want to know what the total cost from V sub S, which was B, to F is, that's just 9. And the question here is, you can stop when you have marked the destination as true. If your goal is to just find the shortest distance to this F vertex, if I don't need to know more information for later use in the graph, as soon as I've marked the destination vertex as true, it is never going to be improved. In some cases, you can stop early. In this case, since it was the last one, I wasn't able to stop early. So yes, I can go that route. All right. Another way to look at this is kind of like this. And here you can see how we've replaced the graph edges with directed edges from node to parent of node. So those kind of directed backwards. And so you can see how you could sort of back trace your way from F to B. And those arrows now show the direction of travel. And instead of having edge weights, we've replaced with the values from the Dijkstra's table to show the total path length. So the total path length from B to F is 9. And to find out what that actual path is, you sort of backtrace through there. And so that's what we thought. We saw B, A, C, E, F early on was our best path. And that has confirmed it. So in terms of Dijkstra's complexity, I've got a big O of V squared. It's just like Prim's, right? For my simple nested loop version, the only difference is I've got that add of the source cost when I compare a vertex's best distance. So there's a constant amount of additional work every time I do a comparison, so it hasn't changed my overall complexity. If I'm going to go with a sparse graph, I can stick these values into heaps. Stick them into a heap instead of doing the lookup. So I end up with an E log V. And you can check CLRS for a good explanation of that. So it ends up E log V because I am going to consider every edge. I don't have to consider more edges than I have. With sparse graphs, remember, we have fewer edges. E is smaller than V squared, right? So if I've got much less than V squared edges, I would just want to do something that was more edge slanted than something that's more vertex slanted, right? When all of the vertices are connected, or I've got something that's very dense, then the number of vertices is what's driving this, so it ends up V squared. But with a sparse graph, I can stick each one of my new edges into a heap, and I will pop out the best edge instead of having to do the loop, sort of the first loop in Prim's or Dijkstra's where I'm finding the one with the shortest distance. So I can replace that loop by sticking things into a heap. And then what the heap is going to do is give me the one with the smallest value that's next. So I don't have to do that lookup. But I do have to do the V, sort of the log V cost insertions into the heap. And so I don't get away from that. But in the worst case, each one of those edges gets stuck into the heap. And there's V of those. Worst case, average case, I end up log V is the cost of my insertion. And there's E insertions, E times log V. Here's Dijkstra's algorithm in pseudocode. Sort of look at our complexity as we sort of build up Dijkstra's algorithm. So I've got to take this graph and my starting vertex. That's what the algorithm gives me. And I got an initialization step. I've got to create n as getting the number of items in my vertex set. I can do that in a constant amount of time. I got to create a table which stores those KDP. I have to initialize each one of those things to false and to infinity and to unknown. So that's going to be a linear amount of work. I can create an empty heap in constant amount of time, setting some initial value to 0 and do that in constant amount of time, and then inserting something into an empty PQ. Those all get done in a constant amount of time. So there's how my setup goes. It takes me V to set things up. Here's the heart of the loop. It's got that project 1 feel. While the priority queue is not empty, keep doing some stuff. Take something out. If I put some things in there, then it's going to keep me going. But when I get to a situation where I don't put any more things in there, I'll eventually pop my way out of this algorithm. So as I get the minimum item, which is take something off the heap, right? I'm trying to find the next shortest edge or the closest vertex to investigate. So I'll do that by taking something off of the heap. So I'll get that by saying V sub O is equal to get min. Then the way that the heaps work, as I put something into the heap and I put it in there, so say I can reach a vertex from 3 different locations. The first time I see that vertex, I'll put it in with its distance. So if I've got something that looks like this, right? Here's some vertex D, and say I can get there from A, B, and C. Right? That's an A. I might put this edge in there, put that edge in there, and that put edge in. So let's call this one a weight 4. Let's call this one a weight 3, and we'll call this one a weight 7. So when I discover this, I'll end up putting 4 and 3 and 7 all into my PQ. Right? That's what the heap is for. And it's going to give me back the most important one, which is the shortest one first. So the 3 is going to come out, and then I'm going to use that because that's the best way to get to D. So I'll mark D as known, but I will still have the 4 and the 7 that live inside the heap. So that's where you see this if statement right here. If this thing is not known, well, when I pop D out the second and third time, because they are longer edges, I can say this thing is already known, ignore it. All right? So if the table at that new vertex, my minimum vertex, is not known, then this means I've gotten to the closest way to get to it. Then I'm going to mark it as true, so any other ways later, don't try it. And then for each of the things adjacent to that vertex, if the cost to get to the source vertex plus the new edge is less than what's already there, we're going to update that distance, update its parent, and insert that edge back into the priority queue. So this is the heap or priority queue version of a Dijkstra's algorithm, which you could also use as a Prim's algorithm. All you have to do to make this a Prim's algorithm is remove that sum right there. So you can see how this is going to have the exact same complexity as Prim's, because all I'm doing is changing a constant amount of work inside my inner loop. So it's not going to affect anything in terms of loops. So you can see how the complexity of Dijkstra's and Prim's is going to be identical, right? And so here, as we look at these, as long as the PQ isn't empty. In the worst case, I've inserted all of the edges. So that's going to be, in the worst case, big O of E times through that outer loop. Getting the min value out of a heap requires me to break the heap. I got to take the thing off the top. So I can fix that in log E time, worst case. Then some constant checks and assignments. Then this for loop goes on. How long does this for loop go on? Well, I've got to do this for every vertex. That ends up being a big O of 1 plus E over V. Because remember, I'm going through this. I'm only going to use this in a sparse graph situation. So use this in a sparse graph situation because this is more edge focused than the vertex focused two loop prims, right? So this is a sparse version. You wouldn't use the priority queue or the heap when you're using a dense version, because then you would have V squared items inserted into your priority queue in the worst case. And that's going to be a lot more work. It's actually faster that way to just go do the lookups in the linear time, because it keeps it at V squared instead of V squared log E, which it would be. All right. Everything else in here is pretty straightforward. And in the worst case, when I insert something in a priority queue that has E items in there, on average, I'm going to be looking at, sorry, I say worst case. It's average case. On average case, there's going to be E items in that priority queue, and I insert a new thing in there. It's going to cost me log of E to do it. In the end, I'm going to build this edge set as I work my way through the items in T. I've got this big O of V work. So for each one of my vertices, I'm going to go and figure out if those edges are there. And that is, I thought I had an extra thing after this. This is gone. All right. So here's our exercise. Here's where I'm going to give you time to do this on your own. But to get that time, all you do is hit pause on your video right now. Meanwhile, I'm just going to go right into the solution. So I'm going to try to find the shortest path from O to T. And I like to do these by figuring out what the actual answer is using the human works before we start trying to do this, so we know when we go too far afield. And it looks like my shortest path from O to T goes OA, B, D, T, right? So I'm looking for something that's got a weight of 13. Anything longer than 13 is going to be suboptimal. All right? So to get there, I need to set up a table that gives me O, A, B, C, D, E, F, and T. And I've got a K, D, and P. And since I'm starting at O, let's start out at O here. That's not right. Let's start out with O there. Anything that's in this column that's not noted, that's going to be false. Anything in this column that's not noted, that's going to be infinity. And anything in the third column means it has no predecessor. All right. So as in prims, we're going to mark this as true, find all the things next to it. And O is next to A, B, and C. So plus 0 on A, B, and C gives me 2, 5, and 4. And I did that in the wrong spot again. I'm having issues here. There we go. There we go. All right. So now, as I mark that one, what I can do is go and update the distances to A, B, and C, which end up being 2, 5, and 4, right? And they all come from O, so I'll update O in there. And since O is already being done, I'm going to use that one as true. All right. We go through the loop again. The loop says find me the shortest false. That's, of course, A. So I'll mark A as true and add 2 to the source values from A can get me to B, D, and F in 2, which is an improvement, right? And get there in 4 going through A. Can also get me to D in 2 plus 7, which is 9. That's an improvement over infinity. And that comes through A. And it can also get me to F 2 plus 12 for 14 coming through A. All right. That's my last step in the inner loop. And I'm going to go back to the outer loop. Find my next shortest one. In this case, I've got a situation where I could take B or I could take C. Right? Because both of them have a distance of 4. In the slides, I'm only going to take one of them. You should try taking the other one and see if you still end up with the same answer. All right, so I'll take B as the closest and mark that as true and try to update distances from B with a source value of 4. So B can now get me to C, D, and E. It can get me to C in 4 plus 1, or 5, which is not an improvement. It can get me to E in 4 plus 3, 7, which is an improvement through B. And B can get me to D in 4 plus 4, which is an improvement. I can get there in 8 coming through B. So there's all that B can do for me. And next up, I'm going to find my next shortest vertex, right? And that's going to be C, because I can still get there in 4. So if I mark C as true and see what C can update for me, C's got a source weight of 4 already, but C can only reach E in terms of things that are already that aren't already known. So C to E and 4 plus the 4 to get there is 8, and I can already get to 8 to E cheaper than that, so there's not even anything new that C shows me. So then I move on. Find my next shortest vertex is E, so we'll mark that as true. That's got a source distance of 7. So I'll add 7 to what E can reach. E can reach D in 1. So 7 plus 1 is 8, which I already have an 8. You could update that if you wanted to, but that's additional work that's unnecessary. So I'm not going to update it because it's not an improvement. So I don't make any changes there. And E in 7 plus 7 more to T looks like 14. That's an improvement. It's better than infinity for sure. But we know that the final answer is going to be 13, so we're not done yet because we still haven't marked T as true. My next closest vertex is going to be D. We'll mark that as true and see what D can update for me. D is only adjacent to E and T. Well, E's already marked, so it's really only adjacent to T. So D's source value of 8 plus the 5 to T gets me there in 13, and that goes through D. As previously mentioned, once I mark this next one, because my shortest one in this case is going to be this T for 13, I'll mark that as true. I could stop here. I know that the total distance from O to T is going to be 13. It's not going to get any better. I do, however, have the chance to update F, and I don't update F in this case because the distance to T is 13 plus 3 more to F isn't an improvement. I end up marking this as true eventually with no more updates. So there is my graph. If I want to figure out, my Dijkstra's table, if I want to figure out the distance from O to T, I can see it right here. It's this 13. If I want to figure out that path, it goes from T back to D, goes from D back to B, goes from B back to A, and it goes from A back to O. And as we saw earlier, OA, BDT, that is my best. It is 13. Dijkstra's has 1. We have 1. We're good. All right. Little bit of one more thing to check out here as we're talking about shortest path problems. So far, we've been looking at the single source shortest path problem. There's one more problem that's quite a bit different. It's the all pairs shortest path problem. That means I want to know the shortest path from any location to any other location. One way to do that is, of course, run Dijkstra from every source location. That takes something that looks like it's v squared in the worst case, and I do it v times, and end up with something that's v cubed. That sounds terrible, but that's what it costs. There's some other solutions. We would, if we had a dense graph, we would use Floyd's algorithm in replacement of Dijkstra's algorithm v times. Floyd's algorithm is v cubed. All right, so there's not an improvement there. If I've got a sparse graph, I can use Johnson's algorithm. It's going to be slightly faster than the V cubed, but not things that we're going to be discussing here today, right? So Floyd's algorithm would do the same thing as Dijkstra's algorithm. It's a lot of fun to look at. So much fun, in fact, that we have slides for it. And that's actually the colloquial name, Floyd's algorithm. It's really the Floyd-Warshall algorithm. You don't need to know it for the exam. It's a really cool DP solution to this problem, though. So you should, with some free time, check out the Floyd-Warshall algorithm. It's kind of a little twisty there because you have to sort of take dynamic programming for what it's worth, right? It says if I've got the best solution, I can extend that solution to get another slightly larger optimal solution. So that's where we're going to leave off and check out some things. We've talked about some things to do, some things to retry things, some algorithms to try to rewrite, some understanding there. Hopefully we move you forward. All right, we'll take this over to the Google Meet if we have any more post-lecture questions.